Hello and welcome to a demonstration of some of the latest developments in Cisco's timing and synchronization portfolio. My name is Dennis Haggerty and I'm a principal engineer in Cisco's mass scale infrastructure organization. Today we'd like to share some of the improvements that we have made to the products and solutions being developed to help solve communication problems for our customers and partners. As we all know, the timing and synchronization of devices and applications is becoming increasingly important for many industries and use cases. As our reliance on timing increases, so does the importance of being able to ensure increased resilience of the clock sources and oversight of the whole timing distribution network. There are several aspects that we will share today, and they can be broken down into the following categories. PRTC-A versus PRTC-B Grandmasters, improving the accuracy and the reliability of Grandmaster nodes. Second, passive port monitoring, using the network to monitor itself for problems in timing distribution and network anomalies. 3. Advanced port monitoring, using routers with embedded GNSS to monitor time accuracy at the edge of the network. And 4. PTP Performance Monitoring, using the latest G.8275.1 features and Yang models to confirm the performance and accuracy of clocks throughout the timing distribution network. So first, a little background on PRTC-A and PRTC-B. What are they and why is it important? PRTC stands for Primary Reference Time Clock, which is a source of frequency and time. The terms PRTC-A and PRTC-B come from the ITU-T standard G8272 that defines various levels of performance, in this case Class A and Class B. One of the key differences between a Grandmaster based on -A and one based on -B is the level of accuracy and resilience they provide. PRTC-A is designed to deliver a maximum time error of 100 nanoseconds relative to UTC, which has been the standard for many years. However, as networks evolve and applications become more sensitive to timing and accuracies, PRTC-B offers a significant improvement by reducing the maximum time error allowed to just 40 nanoseconds. Additionally, PRTC-B introduces stricter requirements for robustness, enhancing the stability of the timing network under varying conditions. This increased precision helps ensure that next generation services receive the most accurate timing possible. Traditional single band GNSS receivers operating only on the L1 band are more susceptible to ionospheric delays and interference, which increases timing errors because they typically rely on a fixed ionospheric model, limiting their accuracy. By using both L1 and L2 bands, a PRTC-B Grandmaster can directly measure and compensate for ionospheric effects, significantly improving stability and precision. A key enabler of PRTC-B's improvement accuracy is the use of this dual band GNSS reception, levering both of these frequency bands. This isn't just a feature of a single constellation. There are multiple bands transmitted by the most widely used GNSS systems, such as GPS, Galileo, GLONASS, BioDow, and others, and the Cisco 8000 supports multiple bands in all these constellations. This capability is particularly valuable in urban environments, where multipath interference, jamming, and GNSS signal degradation pose challenges to maintaining accurate timing. Receiving these GNSS signals across two bands also assists the receiver to detect and resist jamming and spoofing attacks. The result is a more resilient and reliable timing source, ensuring that networks remain synchronized even under very demanding conditions. Let's look at the topology we will be using to demonstrate these capabilities. We have 3 Cisco nodes. First, we have Columbia, which is a Cisco 8011 fixed 1 rack unit router acting as a PRTC-B and Grandmaster. Secondly, we have Everglades, which is a Cisco NCS 540 router acting as a PRTC-A and a TGM. And then we have Zermatt, another NCS 540 of the same model, acting as a TBC or boundary clock. Although this is configured as a boundary clock, it is also equipped with an embedded GNSS receiver. As explained later, this receiver is configured with what's called a PTP virtual port, a mechanism that allows PTP to use its local GNSS as a source of time. We have additional equipment in place to assess the performance of the Cisco network clocks. First, we have an enhanced PRTC, an enhanced primary reference time clock that provides a higher level of accuracy than the router nodes. This clock benefits from being conditioned by a cesium-based atomic clock, further improving long-term stability. Both this ePRTC and atomic clock are manufactured by Microchip. All the devices share the same L1, L2 antenna system, and cable length differences are calibrated out. To measure the timing performance, we use a Calnex Paragon Neo timing tester. The Paragon Neo can analyze precision time protocol, synchronous Ethernet, and 1 PPS signals from the network devices, comparing them against reference signals from both the atomic clock and the ePRTC. This allows us to validate synchronization accuracy and performance across the network. Looking at the results, here is a graph showing the time accuracy of the Everglades PRTC-A taken during a 12-hour overnight run. The data was collected by the Calnex from the 1 pulse per second output port on the Everglades and processed by a low-pass filter. The green lines at the plus 100 and minus 100 nanosecond mark indicate the performance limits for the PRTC-A. This device shows a mean value of minus 68 nanoseconds compared with UTC time determined by the ePRTC. The peak-to-peak variation is approximately 46 nanoseconds, demonstrating the slow wander of the time caused by diurnal effects of the sun interacting with the ionosphere. There are similar values obtained if one measured PTP output rather than 1 PPS. This level of performance is typical for a GNSS receiver with a PRTC-A level of performance. So what about the PRTC-B? How does it perform in comparison? We took the measurements from Columbia during the same overnight run as the measurements from Everglade. The data was collected by the same Paragon Neo from a 10 gig PTP port on Columbia and again processed via a low pass filter. Although the Everglade result is 1 PPS and the test is measuring PTP, previous testing shows the difference between the two measurement methods is negligible. The green lines at plus 40 and minus 40 nanosecond mark indicate the performance limits for PRTC-B. Columbia shows a mean value of almost 0 nanoseconds compared with UTC time, while the peak-to-peak variation was around 31 nanoseconds. Compare that result to the minus 68 nanoseconds mean and peak of 46 nanoseconds for the NCS 540 Everglades. That's a significant improvement in relative accuracy and reduction in peak-to-peak variability. Although both devices use the same antenna system, Everglades only processes L1 data, while Columbia uses both L1 and L2 bands. We will come back to the relative performance offset between these two devices in a moment. But it's clear that under real-world conditions, the PRTC-B built into the Cisco 8000 series will be much more accurate and stable under the same conditions as the previous generation PRTC-A receivers. As part of the support for the L2 band, Cisco enhanced the CLI output to show not only the constellation but the individual signal bands that the receiver is receiving and processing. This output from the Show GNSS command shows recent output for receiver in the Cisco 8000 configured to use GPS. In this output, the receiver shows that the space vehicle with the PRN number 5, highlighted in green, is receiving signals on the L1 band, the CA signal, and the L2 band, the L2C civilian signal. However, Space Vehicle 13, highlighted in yellow, is only transmitting on the L1 band, which indicates it is an older satellite that doesn't support L2. Currently, only 25 of the 32 GPS satellites support L2. Making this extra information available will improve the operational visibility for operators and ensure the receiver is using all the signals available to it. The next feature is one that is useful for managing the timing distribution network. One of the key issues for the operator of that network is how can they be sure that the network is transporting and recovering the time accurately and in a stable manner. The ability to detect offsets between different chains of clocks will alert the operator of any inconsistencies that would indicate an error in the timing distribution network. When the PTP clock first becomes active, it listens on all its PTP ports for PTP announce messages sent out by the other PTP time transmitters. It then uses the best time transmitter clock algorithm, or PRTC-A, to determine which of the reachable sources of clock is the most accurate and the least number of hops distant. Let's compare the information between them. The clock information from PRTC-B Columbia, highlighted in green, shows a higher clock accuracy, hex 20, than that hex 21 of PRTC-A Everglades, which is highlighted in yellow. The lower the number, the more accurate the PRTC. Therefore, as confirmed by this output, the PRTC-A running on Zermatt will select the port connected to PRTC-B to be the time receiver or slave port. The other port will be placed in either master, times transmitter, or passive state. Now PTP is using the T1 to T4 timestamps from Columbia to discover the time. This output shows the state of the servo and how it is phase locked to the PRTC-B Grandmaster and is reporting a phase time accuracy of 3 nanoseconds. Note that this self-reported phase accuracy is liable to change up to 16 times a second with every new set of T1 to T4 timestamps. However, the other port, now set to master mode in yellow, is also able to see a source of time and frequency since it's connected to Everglades PRTC-A. It's the passive port monitoring feature that allows the servo running on Zermatt to also collect the timestamps on that unused port and calculate the time using those timestamps. It can then report on any differences between them. Here we see that the primary port, the one actively recovering time, is currently estimated to be within a single nanosecond, marked in green, but that the time recovered from the two ports on Everglade are 54 and 58 nanoseconds, marked in yellow. The clock offset value in parts per billion is a calculated estimate of any frequency offset, although it's not important for this case. This output was taken at the same time as the overnight run above, showing approximately 54 to 58 nanoseconds offset between the two PRTC devices. And this is the same value which is seen by the Paragon Neo during the test when you compare the results at any one time instance. It's clear that this value is still very acceptable since it's within the range of the possible time error values produced by the PRTC-A. If it was more than, say, 140 nanoseconds off from the PRTC-B, then it would indicate a potential problem in the timing sources or in the timing distribution network. For that reason, Cisco now supports the ability to set a threshold on the received values and to alarm should that value be exceeded. This output shows such an alarm being generated in yellow and then cleared in green. It is also possible to monitor those values via a Yang model and display the output via a graphical user interface, such as shown here. To produce this graph, the PTP time offsets for the time receiver and the passive ports are pulled using Wang and displayed. The blue line is the primary port, while the green and yellow lines are the passive PTP ports. The graph demonstrates an interim drift in the PTP source at the green passive port, indicating there's a problem in the time recovered from that clock. The magnitude of the drift is easily detectable relative to the router's own blue clock and the other available source shown in yellow. In this scenario, we induced a clock drift on the primary PTP source, indicated by the blue line. Since the PTP algorithm keeps adjusting the router's clock to follow the PTP transmitter, we do not see any variation in that blue line. However, the problem with the primary port becomes evident because the other green and yellow lines are all moving by roughly the same amount, indicating an inconsistency in time signals that would require investigation. This CLI output shows the same situation. This is an important development for managing and assuring timing distribution networks. it makes sense to use the interconnectivity and the redundancy built into modern networks to ensure that time is consistent across the network. This feature is proving very useful, particularly in access rings or in any form of mesh network. But what about if we could take it to the next step and measure the time in the network against a trusted source of time? In the timing industry, a device that can do this is known as a PTP probe. So if we have a standard router with a GNSS receiver, it would be helpful to be able to use it as a PTP probe. Sometimes the router's GNSS is used as a local source of timing signals for on-site use. Other times it is unused. With this new feature, it is possible to make use of the local GNSS to measure the time accuracy of the timing distribution network. This feature is based on one of the latest features to be added to the ITU-T G.8275.1 standard, which is contained in Annex G, monitoring alternate time transmitted time information provided by a peer PTP port. So what is advanced port monitoring? With this feature, it is possible to strategically select ports that provide assurance information to a peer PTP port and select those which will receive and process that information. This is an extension to the basic passive port monitoring above, which when that feature is enabled, works on up to 4 passive ports automatically. But with this extension, the operator can define the ports based on the most useful topology. An additional capability is that it is possible to define the local GNS as a virtual PTP port that will enable the servo to receive time information from a GNSS constellation, either as a primary source of time or as a redundant backup. This virtual port feature has been available for some time in the ITU-T standard 8275 as Annex B. But with this new feature of advanced port monitoring, the GNSS-equipped node can now use that satellite information to report any PTP time offset seen between GNSS and the PTP time signals back to the operator. Again, using a simple ring as an example, notice that we are now using a completely separate source of time as a measurement tool. Because the comparison is now network time against time recovered from the satellite, it will now also discover errors in the source of time from another PRTC, such as that from a misconfiguration of the antenna cable length. Here's a demonstration of advanced port monitoring of a PTP source with data captured through Yang models and displayed. The Cisco router is locked to a PRTC clock and is monitoring the time offset of the available PTP source. Asymmetry is introduced on the PTP port for a short time, causing the time offset to increase until the node raises an alarm that the configured threshold is exceeded. PTP Performance Monitoring. To ensure the accuracy and reliability of timing distribution, the PTP Performance Monitoring provides continuous visibility into the behaviour of the PTP within the network. The newly adopted Annex F of ITU-T G8275 defines a framework for collecting key timing performance metrics, allowing operators to assess the quality of synchronization in real time. What is PTP performance monitoring? This monitoring of the PTP clocks involves gathering information such as path delay variations, packet timing errors, and clock stability metrics across different network nodes. The data is collected in structured time intervals, with key statistics stored in 3-minute and 15-minute measurement windows. The 3-minute buckets provide a short-term view of PTP performance, capturing fine-grained variations in packet delay, timing errors, and clock drift over the previous 1 hour. This allows operators to detect sudden changes or anomalies that may indicate transient network congestion, asymmetries, or hardware issues affecting synchronization. The 15-minute buckets, on the other hand, offer a longer-term trend analysis, helping to identify patterns in timing performance over a more stable period extending up to the previous 24 hours. By comparing consecutive 15-minute windows, operators can track the consistency of synchronization, evaluate drift over time, and correlate timing issues with network events. This structured monitoring approach provides both immediate detection and long-term oversight, enabling operators to proactively manage synchronization reduce troubleshooting time, and ensure compliance with strict timing requirements. With these deeper insights into PTP performance, operators can fine-tune network elements, improve fault detection, and enhance the efficiency of timing distribution, ultimately leading to more robust and reliable time services across the network. Here is a snapshot of the performance monitoring data captured through Yang models. Only the 15-minute buckets data is shown for simplicity, but the same data can be retrieved for 3-minute buckets as well. The performance metrics available from the Cisco router captures important information about the PTP clock. It includes the forward and reverse path delays, offset from time transmitter, and the mean path delays observed by the PTP algorithm. Similarly, the performance metrics also capture the per-port statistics of the PTP packets. This includes the sent, received, and drop counters for each of the sync, delay request, delay response, and announce messages on the port. There may be cases where the measurements done in a bucket are not valid. For instance, an interim loss of PTP synchronization. Each bucket carries a measurement valid flag, which in such cases indicates that the measurement should not be considered for analysis. This information is very useful to easily detect any abnormal variations in the timeline and help in pinpointing the location of the fault. So in conclusion, today we have explored 4 key features that help operators enhance the accuracy and resilience of their timing distribution networks. Firstly, upgrading from PRTC-A to PRTC-B for improved performance and robustness. Second, passive port monitoring, enabling the network to monitor itself for timing issues. Third, advanced port monitoring, using routers with embedded GNSS to verify the time accuracy at the network edge. And finally, PTP performance monitoring, leveraging Yang models to assess and optimize network synchronization. Each of these capabilities ensures that timing is delivered with greater accuracy and resilience, giving operators the tools they need to maintain reliable synchronization across their networks.